You can see my screen?
Yes, ma'am.
Okay. Let's start today's discussion. Good evening. Today is the fourth week of the problem solving session of power electronics applications in power systems. So, just to recapitulate our last discussion, in our last class, we solved the numerical problems um, on the active power and reactive power of the sending end side and the receiving end side, right? And uh, we also calculated the angle, the phase constant, and also the active and reactive power at some random point in the transmission line. It may be at any point, like some x kilometer away from the sending end or x kilometer away from the receiving end. So all those things we discussed in our last session. In today's session, uh, so the the idea was to have a have a preliminary concept of the transmission line parameters and to have an idea how to calculate the active and reactive power. And the objective of solving all these things was uh, to get a pretext of why at all we need to learn all this, because the subject is applications of power electronics in power systems. So basically what we will learn is the reactive power compensation in the transmission line, why we require it at all. So that you will we will discuss today. What is the requirement of reactive power compensation exactly, and how will we do that, and after reactive power compensation what is the advantage, what is the benefit we get. All these things is the topic of week 4, right? So I shall briefly discuss about the concepts, and then I will start the numerical problems. Okay. Again, I will not go into the derivations because you already have access to the lectures. There you can see the lectures and you can have an idea how to derive all the formulas. I shall just touch upon the expressions, and then I shall start discussing the problems. Okay. So basically, if this is a transmission line, and here we have the sending end and receiving ends. We have the sending end and the receiving end points. And suppose VM, this point, this is the midpoint. This point is at equal distance from the sending end and equal distance from the receiving end. This is exactly at the midpoint of the transmission line. What we will have to do is we will have to find out the expression of voltage and current at this point, and also later we shall see the active power and reactive power at this point, right? Yeah. So first of all, we need to take a reference, right? So if we want to represent the midpoint voltage as a phasor, then we shall represent it like this: Vm, which is the amplitude, and the angle is minus delta by 2. So this is the sending end voltage is V0, and the receiving end is V minus delta, and the midpoint will be Vm minus delta by 2. So always the power is transferred from the leading voltage towards the lagging voltage. So this is the leading voltage, this is the lagging voltage, and because this is in the midpoint, so this is also lagging the sending end voltage by an angle of minus delta by 2. And you can represent the sending end voltage by this Vm and Im, and the receiving end voltage also by this Vm and Im like this. Okay. After after you just substitute all these values, so if you just if now for now one thing, if you want, you will have to remember that whatever discussion we are doing here, we are always assuming that the line is symmetrical, lossless. Okay, that you will have to remember. For lossless line, there is only reactive part, there is only reactance in the transmission line, there is no resistive part. So the obviously the active power will be same throughout the transmission line, as we already discussed in the earlier session. And another thing is symmetrical. So what does it signify? If the line is symmetrical, then the sending end voltage and the receiving end voltage magnitude will be same. If this is V, this will also be V. I am talking about the magnitude, okay, not the phase angle. The phase angle of this will be lagging the sending end voltage obviously, but the voltage magnitude here and here will be same. Okay. So that signifies that the line is symmetrical. Now, if you do the analysis, you will get the uh, expression of this midpoint voltage and the midpoint current. Okay, something like this. And if you observe carefully, you will see that the phase angle of midpoint voltage and the phase angle of midpoint current, they are equal. So the voltage and current, they are in phase. The angle here is minus delta by 2. Here also the angle is minus delta by 2. The voltage and current, they are in phase. So at the midpoint there is no reactive power. As they are in phase, there is no question of reactive power. Only active power will be there. But this is particularly at the midpoint, not the other points. This particular this particular thing only happens at the midpoint where the voltage and current, they are in phase. And if you have seen the lecture, you must have seen this plot. The plot is in the x-axis, we have the load, but in per unit. We have expressed this in per unit, and the base power is the surge impedance loading. In the y-axis, we have the midpoint voltage. So as the line load increases from 0 to the then up to the rated load, then the midpoint voltage varies something like this curve. At no load, there is an over voltage. This is the base voltage. This is 1 per unit. So in the no load condition, there is over voltage, and gradually this decreases at surge impedance load. This is exactly equal to the base voltage, obviously because at surge impedance loading, the voltage is equal throughout the transmission line, but this is a special case. And at the rated load, we have under voltage. The voltage decreases below the rated voltage, right? So this is the plot. Okay. Yeah. Now we can find out what will be the active power and reactive power at this point. Okay. So reactive power was 0 when there was no compensation. So for uncompensated line, the active power and reactive power we already know. We have already derived. But when you have compensation, there is a midpoint compensation. What is exactly compensation? So you will either inject or absorb reactive power, right? That is reactive power compensation. You can either inject it when there is a requirement here, or you can absorb it when there is excess reactive power. This line, this is producing, the line is producing, then you will have to absorb it. Okay. That's how we will compensate the reactive power. Now, now I want to, yeah, before we proceed, just to clarify one thing that see, in the no load condition, you know that the value of delta is 0 degree, right? So cos delta by 2, this will become unity. This is 1. And in the denominator, you have cos beta L by 2. So you can understand at no load condition, the voltage will obviously be higher than the rated voltage because you in that this is less than 1. So this value will be greater than 1. The midpoint voltage will be greater than 1, right? So that's why sometimes this voltage becomes too high, and that is not at all desirable because your the insulation can break, right? So the line insulation is designed for for a particular voltage. If there is over voltage, there will be some breakdown may happen. So this is not actually this is not desired at all. That's why we need to do midpoint compensation. What it does, it is, suppose the arrow is in this direction. Suppose we assume for now that it is injecting power. So it will inject power in this side also. From the midpoint, the reactive power will go here and here. And therefore, the total power that it will have to inject, QC, that is twice QM. The expression of QM is like this, and QC is twice QM. And how we will find QM? QM that we already saw in our the last class, the same way we found out for the normal case. This is the imaginary part of SM, right? The imaginary part of SM is QM. And what is SM? SM is, this is the apparent power, PM, and then IM star conjugate. Okay, so this is my apparent power. If you substitute the expression of Vm and Im here, then you will get Qn. Just separate the real part and imaginary part. Okay. And also the active power also doesn't remain same. Active power also changes. Now you may question, we are doing reactive power compensation. Then why does the active power change? The active power changes because the voltage here will change. Without compensation, whatever voltage you will have here, after compensation, definitely the voltage will change, right? Because that is our intention, to prevent the over voltage or under voltage over here. That's why the moment you are changing the voltage, then the active power will also change. This is the active power when there is no compensation, but this will change when there will be the line will be compensated. Okay, the expression will change. That we will also see when we will solve the numericals. So and there in the lecture, the shunt compensation and series compensation methods are also discussed. That you can go through the lecture and you will see how we do the shunt compensation and how we do the series compensation. Okay, what is the difference? What is the most effective one? More effective? That all these things you can see in the lecture. Okay, so now I shall start the numericals. So this is the first problem. A 735 kV, 850 kilometer, 50 hertz symmetrical lossless line whose line inductance is L equal to 0.857 millihenry per kilometer. Line capacitance is C equal to 15.4 nanofarad per kilometer. A compensator is designed that will maintain the midpoint voltage at 1.05 per unit, irrespective of the load. So this is very important. Whatever be the load, if you design the compensator properly, it will always maintain the midpoint voltage at 1.05 per unit. That means the over voltage will be only 5% extra. 5% over voltage will be there. It will not cross 5%. Okay. After compensation. What is the voltage at midpoint at no load without compensation? When there is no compensation, what is the midpoint voltage at no load? Right. Okay. So, okay. So let's start. Now, now we need to find out the midpoint voltage when there is no compensation. So the midpoint voltage expression is this. A cos delta by 2 cos delta by 2 by cos beta L by 2. Right. This is the midpoint voltage expression when there is no compensation. At no load, we need to find out. So obviously delta will be 0. Delta will be 0 degree. And this becomes unity. This portion becomes unity. And they have told to find out in per unit. This is the voltage amplitude in sending end as well as receiving end, because this is a symmetrical line. And they have we need to find out at per unit, so we can anyway divide this value. So this will be the per unit will be cos delta by 2 by cos beta L by 2. Cos beta L by 2. Okay. And at no load, the numerator becomes 1. So 1 by cos beta L by 2. Right. Now what is beta L? Beta L is this we already know, we have solved this multiple times. Beta is omega root LC and we need to multiply with the length of the transmission line. So 850. 850 kilometer is the length. Then we will find after doing this calculation, we will find beta L in radian. Okay. So can you solve this portion and tell me what is the value?
0.96.
0.96. Okay. 0.96 radian. And if we convert it in degree, what will be the value?
55.03, ma'am.
55.031, right?
Yes, ma'am.
Okay. Okay, so this is in degree. We have found out beta L, so beta L by 2 you can obviously find out. Then what is this value? Then calculate. This this expression you calculate.
1.127 is the answer, ma'am.
1.127. So I got 1.13. They are close. 1.13. So option B is the correct one, right?
Yes, ma'am.
Okay. So let's go to the next problem. What is the expression of active power of uncompensated line? This is very easy. Uncompensated line means they are the usual one that we solved in the last class. The same expression we need to find out. Right. This is question number 2. We need to find out the um, active power. What is the active power of the uncompensated line?
Two seven nine four point six two two sine delta, ma'am.
Okay, just a minute. I will just write it. So P equal to will be, I am not writing Vs or Vr separately because their amplitudes are same. So this will be V square sine delta by rate C sine beta L. What was your answer?
2794.622 sine delta.
2794.62 sine delta sine delta. Right. Okay. Just a second. 2794. Okay. But I think I found out 2776. Okay. Just go through your calculation once more. So V square is V was given 735.
735.
Right. So this is 735 square. And what was your ZC value? Characteristic impedance?
235.9, ma'am.
235.9. Right. So I also got the same figure. Right. So only remaining thing is sine beta L. So sine beta L was the beta value I got 55.568. So it was 0.824. This I got. So into 235.9 by square divided by answer. So it should come 2776. Okay. I think just try to take a few more decimal points, then you will get to the exact value. Because, right. So when you are calculating beta L value, just try to take a few more decimal points. Then I guess you will get to this answer. So option C is the correct option. Okay.
2778.5, like that is
That
near
is,
to 2776.
yeah, that is close enough. If it is 2778 also, then you will be able to understand this is the closest one. But suppose if you get like 27, like earlier you told some other answer, then it will be a problematic, right? Because then you will get confused what is the correct answer. So if it is like a bit different, it is okay. You can find out the close option. Okay, so the third problem is determine the reactive power compensation required to hold the midpoint voltage at 1.05 per unit. Now, compensation is required to maintain the voltage at 1.05 per unit. So, what will be the expression of the reactive power? Okay. So first of all, we already saw that the reactive power required, the compensation required is 2 qm, because it will go towards the sending end as well as towards the receiving end. Right. So 2 qm. This is equal to 2. Then all the voltages I will write they are in line to line. Remember, okay, I am not writing the 3 because I am expressing in terms of line to line voltages. Pm square cos beta L by 2 minus P Pm cos delta by 2 by 3 L by 2. This is the expression of the compensated reactive power, the compensation that is required. Now, beta L value you already know. Beta L by 2 you already know. Pm, we need to restrict it within 1.05 times 1.05 times V, right? So that is Vm, and delta, because delta will be in the expression only, so delta we don't need to know. Delta is not required, and ZC also you know. So just find out this, just substitute the values and then tell me what is the answer. Yeah, did you find out yet? Hello, are you there?
Yes, ma'am, doing, ma'am.
Yeah, okay, okay. Okay, take your time. I will just write the answer that I found out. You can anyway calculate it by your own. It is just substituting the numbers, that's it. So I found out this. Um, I found out this expression.
Ma'am, once show the options, ma'am. I got related to this answer only, but not exact this answer.
Okay, okay. Um,
I got 9695.71 minus 10411.5, ma'am.
okay, so anyway, this is the closest one, right? Option
Yes,
A.
ma'am.
I guess. Okay. Yeah, just see that after you add this compensation, now your midpoint voltage is 1.05 per unit. But earlier in the first question, if you remember, we found out it was 1.13. So that time the over voltage was 13%. It was 13% more than the rated voltage. But here it is only 5% over voltage, right? That is why reactive compensation is important to uh, just to so that there is not the over voltage is not too much. Okay. So question number 4. What is the expression of active power of the compensated line? As I already told you that when you have compensation, the active power also changes. The active power expression also changes when there is compensation. Yeah, so the expression of the compensated active power is this. Oh, this is the expression. So this is not equal to the expression that we were calculating with earlier. That was V square sine delta by ZC sine beta L. They are not equal. Okay, they are different. Yeah. Now please calculate this expression. 'Vm' you take again Vm you will have to take 1.05 times V. 1.05 times V. This is the rated voltage.
5205.8 sine delta Q.
5205
0.8 sine delta 2.
delta by 2. 5205. Hmm. Okay, but I got 51 close to this option C, 5159. Uh, just a sec. So, this is, so if I just calculate this is, this I can write 1.05 multiplied by 735 square divided by 235.9 and sine 27.784 degree. So did you the beta L by 2 angle, did you get this one or something else?
I got 27.51, ma'am.
27.5. Okay, even though we
51.
take, okay, let's take this and see. क्या होता है? 1.705735 square to 35.9 into sine 27.5 you told, right?
Yes, ma'am.
Okay, this is 5207. Okay, that's what I was saying, that you will have to take like decimal more point up to the decimal. So otherwise, what will happen? Na, it will differentiate too much. Actually, I got 27.784 degree. So 735 square divided by 35. So for me, it is coming 5158 point some. 5158.45, something like this. Okay. Whenever you are calculating beta L, this just take uh, at least three points after the decimal. Okay. Otherwise, the answers will not be correct.
Okay, ma'am.
So the correct so option C is the correct option. But you were getting 5207, so you will find this one is closer than this one, right? But actually, this should be the correct answer, option C. Is it fine?
Okay, ma'am.
Uh, Later on, you just calculate the angle beta L and check, okay, whether you are getting this one.
Yes, ma'am.
Next question is, what is the range of midpoint compensator? What is the range of midpoint compensator? Now, how to find out what is the range of midpoint compensator? The range means that, so I told you about the plot. What was the plot? This was Tm by Tc. So this and here it was Vm. The loading, the midpoint voltage versus the loading, per unit loading. The voltage was something like this. If this was the rated voltage, that is at 1 per unit, at no load there was over voltage, and at rated load there was this under voltage, right? The idea is you will do reactive power compensation, and you will do in such a way that no matter what is the load, you will always be able to maintain a voltage which is suppose here for example 1.05 per unit. No matter what is the load, it can be here or here, it can be at rated load, it can be near about rated load, it can be at light load. But whatever be the load, you will always be able to maintain this voltage. Okay. So to maintain this voltage, what is the range of reactive compensation required? You can understand that here we are getting over voltage. So there it should absorb reactive power. The reactive compensator should absorb reactive power at this point, because here the line is generating reactive power. But here the the line requires more reactive power because there is under voltage. So now the compensator has to provide the reactive power. So their signs are different, right? Here and here you will have to provide different amount of reactive power, and their sign will also be different. Here it will be negative, here it will be positive. Okay. So uh, that is what we need to find out, that what is the range. Fine. Yeah. So, so this is simple. What you need to do is, we already found out what was QC. The QC expression we already found out, right? The QC expression was, okay, I will just copy it from here. Yeah, we already found out. This was the expression. This was, sorry, I will just remove this. This was the expression of QC. Now what we need to do is just just put the extreme conditions of delta. At no load, what is delta? At no load, delta is 0 degree. And what is the maximum delta here? The maximum max. So, and then the other extreme condition would be, so del by 2 at max condition, that will be 90 degree. Okay, you need to take it 90 degree. And then you just replace the values of delta and you will get the range of QC. For delta equal to 0, this is unity. So case 1, when delta equal to 0, del by 2 is equal to also 0. So QC for this is 9585.49 minus 10318. So minus 732.51. Okay, that is at no load. We need to take the extreme conditions. And this is at no load. No load, okay. And case 2 is when del by 2 we need to take 90 degree. Then this part becomes 0. This is 9585.49. As you can see very clearly, this is negative, because at this point the compensator needs to absorb the reactive power. That's why this is negative. But here the compensator needs to provide the active power. That's why this is positive. Okay, this is at rated. So this will be the range of QC. Okay, this is the range of QC. The first option, minus 732 and 9685. Okay. Is it understood?
Yes, ma'am.
Okay. This should be 9, not 9685. It should be 9585. So question number 6. If the range of compensation is kept practical, then what is the range of load angle for which the midpoint voltage can be kept at 1.05 per unit? Now, the range that we just found out, minus 732 and 9585, this is an absurd range. Practically, you can't just design a compensator which can work in this much wide range. This is not practically possible. So you will have to kind of reduce this range. That's why this is one practical range where minus 650 to 400. Some practical range that you can design. Okay, this is uh, this is a feasible range. So what is the question? The question is, what is the range of load angle for which in this range of reactive power we can maintain the midpoint voltage at 1.05 per unit. We need to find out the delta corresponding to minus 650 and the delta corresponding to 400 megawatt. Okay, that is the question. This is the question. Now this is very simple again. We already know the reactive power expression, right? You just need to equate this value and this value and find out delta. So QC expression we found out. QC expression again we need to copy this. Yeah. So let's see. This is QC expression that we found out, and you need to just equate this. For the first case, it would be minus 650, and you will have to solve for delta. And for the second case, it would be 400, and again you will have to solve for delta. Okay. So you just solve this and find out the answer. I shall take a break of 7 minutes, and then you can tell me the answer. Okay. Did you find out?
Yes, ma'am.
So what is the
14.5 to 54.19.
delta 1 is 15.52.
14.5, ma'am.
0.
14.52. 14. 54, right?
54.19. Yes, ma'am.
So I guess option B is the correct one, right? Option B. Okay. Now just a little something on this question. So earlier, if you can remember, we found out the QC expression, and we told that in the whole range of delta, we should be maintaining the voltage at 1.05 per unit. And then we found out the expression of QC as a function of delta, right? Then what we saw was that the range we found out for QC, for the extreme deltas, that is at 0 degree and 90 degree, that is not feasible. Practically, it is not possible to design a compensator. Maybe it is possible, but again there is a question of cost. It like if the cost is too much, then it will not be practical again. So we can't maintain the voltage at 1.505 per unit throughout the load. Okay. But what we can do is we can take a practical range like this. We can take a practical range and then we can ensure that for certain portion of the load we can maintain this voltage. And that we found that the range of delta was roughly 14 degree to 54 degree. That is the rough range, right? So when the delta value is within this range, we can ensure that the voltage at the midpoint will not exceed 1.05 per unit. But when delta is less than 14 degree, or when delta is greater than 54 degree, in those portions we can't ensure that this voltage will remain at this, the midpoint voltage will remain at this point, right? 1.05 per unit. So uh, beyond this point, when delta is less than 14 degree, you will still be able to restrict the voltage, but it will not be 1.05, it will be greater than that. Okay, it will be something which will be slightly greater than this value. Okay, and here also there will be under voltage, but not as much as there is no compensation at all. But still there will be some under voltage, but it will not be this value. It will be sorry, huh? So you will be able to prevent the under voltage, but it will be not as effective as the original range. Okay, original range. So that is the point. Yeah. Now let's see the next question. What is the value of the reactance when the compensator is operated in fixed reactor mode? So have you seen the lecture? Have you seen this? What is fixed reactor mode and what is fixed capacitor mode?
Yes, ma'am. In lectures, yes, ma'am. Yes.
Yeah. So can any of you tell what do we do in fixed reactor mode?
Ma'am, in the graph, what you have told before, if the voltage is over voltage exceeds, at that time the fixed reactor will occur, ma'am. After that time, in no load condition only, this fixed reactor it will perform, ma'am. After that time, it will be in SIL mode. Next, after when it is in under voltage, then it will act as fixed capacitor mode, ma'am.
Yeah. So basically there will be some practical range of reactive compensation, and that range corresponds to some delta value as we already found out. So delta equal to 14 degree here, and here it is for 54 degree. So as we already saw, beyond this point we will not be able to prevent to restrict the over voltage to 1.05 per unit, because then the compensator will be like too costly or very difficult to design also. That's why what we do is, beyond this point we just, because here we need negative compensation. It was minus 650 if you remember. So here we need negative compensation. That's why we need to have we need to have reactor, because in that case we need to absorb reactive power. That's why it should act as a overall, it should act as a inductive reactance. Okay. And this will be a fixed reactance from delta equal to 0 to delta equal to 14 degree. It will be a fixed reactance. They are in the question they are asking what is the value of the reactance of the fixed reactor. What will be XL? The value of the reactance that we will put beyond in this range from delta equal to 0 to delta equal to 14 degree. Okay, that is very simple. So here at delta equal to 14 we will be able to maintain Vm at what? We will be able to maintain the Vm at 1.05 times 735, right? 735. And at this point we know what is the QC, or you can also say QL, whatever QC. This is inductive, so this is minus 650, right? Now can you tell how to find out this XL? This is basic power electronics or power system, whatever. This is a basic concept. If you have the voltage and the reactive power, then how to find out this reactance value?
Vm by QC, ma'am.
Pm by QC. Are you sure?
Vm V into Vm's
No,
Vm
if
square.
you
Yes,
do
ma'am. V into Vm.
Vm by QC, does it match with the dimension of XL?
We need to remove the minus sign, ma'am, because it is in
That is okay.
fixed reactor.
We will only take the magnitude. The minus sign is not
Mm.
required. That is fine. But if you do Vm by QC, does it give you reactance? Does it give you reactance? Because
Vm
this will be the dimension of some I, some current, inverse of some current. That is this expression that you just told, Vm by Qc. If you want to find out XL, it would be Vm square by Qc. Just remember, when you find out find active power, you do V square by R, right? Just a resistive load I am talking about. You do V square by R, right? Do you do V by so when if somebody tells you to find out to find R, you will do V square by P, right? You will not do V square V by P. Did you
Yes,
understand?
yes, ma'am. Yes,
Yeah,
ma'am.
Yes, ma'am.
so this QC, the dimension of Q and P, they are similar. Like both of them are power. One is active power, another one is reactive power. But both of them are power. So whenever you will have to find the reactance, then you will have to do Vm square by QC, not V by QC. Okay, this is wrong. Yeah.
Just
What is the answer?
872.67, ma'am.
Sorry, what?
872.67 ohm.
872. Okay. So VM you took this value, right? 1.05 times 735.
Yes, ma'am.
Uh,
I got different answer, ma'am. 916.30.
yeah, I am also getting 916. So
Yes, ma'am.
so the answer is 916. 916. 916 ohm. That is the answer of Excel. Yeah. How did you get 872? Because that is also in the option. Did you take some other value?
Yes, ma'am. I take Excel value is 600, ma'am.
Oh, acha, okay, okay. Just be careful, okay? Because in the exam or in the assignment, there will be whatever you will get by adding some different value, that option will also be there. So right now, if you didn't like you are not cautious, you will end up getting the wrong answer. Okay, so here 872 is also there. See,
Mhm. Yes.
so if you do a slight mistake, that answer will also be there, and you will take the wrong answer. Okay. Okay, fine. So, yeah, okay. This is done. Next question. What is the value of the reactance when the compensator is operated in fixed capacitor mode? So again, the same discussion we had. In this range, when delta is greater than 54, in that portion we need to operate the system in fixed capacitor mode. The compensation will be fixed capacitor, right? Because here the compensator needs to provide reactive power to the system. Earlier it was absorbing the reactive power, now it will provide the reactive power. So definitely it will have to be a capacitive reactance, right? Now again the same thing you will have to do. It will be Vm square by QC, but now the QC value will be different. Now QC value is 400, right? So now tell me the answer. What will be the answer?
1488.9.
So the answer is 1488.9. Okay, so option C. Okay, this is the correct answer. Fine. Fine by everybody.
Yes, ma'am.
Now question number 9. when the compensator is operated in fixed capacitor mode, what is the expression of power flow? Here power flow means active power. Okay. So if they ask for reactive power, it will be specifically mentioned. If there is just power flow, that means active power. Okay. So this question. Yeah. Now one thing, if you see that when you have done compensation, so in that case, for finding out this power flow, the active power, first what we will have to do is you will have to find out the VM. Why we will have to find out the VM separately? Because now they have specified that we are operating in fixed capacitor mode. And whenever you are operating in fixed capacitor mode, VM is no longer 1.05 VM. You can't take this, okay? You can't take this because now it is telling us that now our delta is beyond the range that we found out. Here the VM value will not be this. We will have to find out what is the VM value first. Then only we can find out what will be the power flow. So what is VM? The VM expression will be V cos, that you can find out in the lecture. I think sir has given in the lecture note also. This will be the expression of VM in fixed capacitor mode. Okay, fixed capacitor mode. So minus ZC by 2 XC sine beta L by 2. The only challenging part in these questions is these expressions. They are a bit bulky, that I understand. But anyway, we will have to understand them. And in the question, when you will solve in the exam, you will have to remember these expressions. Okay. Maybe you will not get enough time to derive. If you get the time for to derive these expressions, that is fine. But if you don't get the time, most probably if you will not get the time to derive, you will have to remember. Okay. This is the expression of VM in fixed capacitor mode, and this XC is the reactance value that we just found out. The XC value we found out, which was some 1488, something like that, 1488.89. That you need to replace here. And other things you already know, take beta L as so beta L by 2, please take this value, otherwise you may get wrong answer, 27.784. Okay. Degree. You take this and yeah, and cos delta by 2 will be there. So just the rest of the thing you may find out. If you get this expression, just tell me if you get this expression.
0.866 cos delta by 2, ma'am.
Sorry,
866.
0.833 cos delta by 2. But how we were getting 0.866? Because if you multiply V, the value of V is 735. So it should be 866. This point, how we were getting?
Ma'am, this is in terms of kilovolts, ma'am.
Yeah, this is already in kilovolt. 735 is already in kilovolt. So you don't need to again convert it to, you don't need to divide by 1000. Did you understand?
Yes,
It would
ma'am.
be 866 cos delta by 2 because
Yes.
735 is already in kilovolt and this value will be slightly higher than 735. So it will be 866. Now what is P? That P for compensated line that we already found out. This was VVM sin delta by 2. Sin delta by 2 divided by ZC sin beta L by 2. Sin beta L by 2. Okay. That is the expression. That is the expression. We know what is VM, we know what is V, we know what is ZC, and we also know sin beta L by 2, right? So now here most probably they have given the answer in terms of sin delta. Why? Because if you see in the expression of VM, there is already a cos delta by 2 and here there is sin delta by 2. So if you combine them, 2 sin delta by 2 and cos delta by 2, that becomes sin delta, right? So they have combined them and then they have given the expression. So if you calculate, just tell me what you are getting.
5788.41.
5877.
5788 point.
Five seven 5788.41. Then
Sin delta, ma'am.
sin delta. Are you sure?
This answer only.
I don't think so. Like if you combine it, then it will not be 5788. So see, uh, here we have in the numerator we have uh, 735 and multiplied by 866. 866 cos delta 2. Cos delta 2 delta by 2 and already there is a sin delta by 2. Sin
Yes, ma'am.
delta by 2, right? And then in the denominator I am just calculating 235.9 multiplied by sine 27.784. It comes out to be 109.962. 962. Okay. So 735 multiplied by 866 divided by 109.962. This is what you just told, 5788 something, whatever. But if you combine this, then you need a 2, right? 2, you need a 2. So you will have to divide the number by 2. So it will be 282894 sine delta. Did you understand? You need this
Yes,
2
ma'am.
to make it sine delta. So you will have to divide by 2 also to get the sine delta expression.
Okay, ma'am, now I understood.
Yeah. So the correct expression 2894 I was getting. So option B, I guess. 2897. This is the closest one. Okay. Now question number 10. When the compensator is operated in fixed capacitor mode, what is the expression of midpoint voltage? That we already found out. So this one only, right? This one only. In fixed capacitor mode, remember there are two modes, fixed capacitor mode and fixed reactor mode. Now they are asking in fixed capacitor mode. So VM. This is VM, but they are asking in per unit, I guess. They are asking, no, they are not asking in per unit. This is actual one. So the first option is the correct one, 866.9. Okay, this is the correct option. And then we have the last question. In fixed reactor mode, what is the percentage of over voltage at midpoint at no load? In fixed reactor mode. Okay. What is the percentage of over voltage? I already told you that when we are operating in fixed capacitor or fixed reactor mode, the VM will not be 1.05 per unit. We need to find out the VM. In fixed reactor mode, we need to find out VM. So again, uh, we need to write the expression of VM, which will be, this will be slightly different from the fixed capacitor mode, right? So this will be slightly different. This is V cos delta by 2. Sorry, I think, yeah, no, this is, sorry, there is no 2. Uh, so P cos delta by 2 divided by, this is cos beta L by 2. And here it will be plus, okay. This is plus ZC by 2. Mind it, this is XL, not XC. This will be 2XL, then sine beta L by 2, okay. Sine beta L by 2. When for fixed capacitor mode, this will be XC. For fixed reactor mode, this will be XL, okay. XL value, I think we found out 916 point something. 916 ohm. Okay. So can you find out what will be the VM value?
777.99 cos delta by 2, ma'am.
777.99. But here the cos delta by 2 will not be there because just read the question. What will be the delta value?
No load condition, ma'am.
Yeah, so what
Delta
is
is
the
equals to 0.
delta equals to 0? So only 777.99. This is the point voltage at fixed reactor mode. Now, what is the percentage of over voltage? Quickly find out what is the percentage of over voltage then.
Five 5.84, ma'am.
Right, 5.84. 5.84%. So the rated value is 735 and the midpoint voltage we are getting is 777.99. So this is the over voltage. If you remember, at first in the we got the expression 1.19 1.13 per unit, right? Without compensation, we got 1.13 per unit we got at no load, right? So this was 13% over voltage. Now we are using the fixed reactor operation and we are getting 5.84% over voltage. So this is certainly a significant improvement, right? Compared to the com compared to the uncompensated one. So yeah, so the option D is correct. Okay, 5.85. This is the correct option. Fine. So this was our last question. Does anybody have any doubt to understand any question, any problem that we discussed today?
Ma'am, in week 3 lecture, I have one doubt.
Okay. What is the doubt in problem solving or in general
Problem
concept?
solving. Problem solving only.
Okay, okay. Okay, tell what is the doubt?
One question
Should
is there, ma'am, related
should I
to
open
reactive.
should I
Yes,
open
ma'am.
last okay, I will just open. Right. Yeah, question number, which question? Okay, I will just show you. Just tell me which one. Okay, I will one by one I will show.
Yes, ma'am. Ma'am, question number 6, ma'am.
Question number 6. Okay. Determine the reactive power at 400 km from the sending end considering symmetric operation of the line and rated load. See, today also we discussed that
Yes, ma'am.
if you remember today at the beginning of the session, we discussed the expression of midpoint voltage and midpoint current, if you remember. So there, uh,
Both voltage and current are in same phase. That one only, right, ma'am?
yeah. So there, both of them are having the same angle,
Same
phase
phase.
angle. So from this only you can understand if voltage and current they are in same phase, there is no question of reactive power, right? If voltage and
Yes,
current
ma'am.
are in same phase, then sine phi becomes 0. So there is no reactive power. That's why in this question, it has been asked that at 400 kilometer from the sending end, and the line length here was 800 kilometer. So at 400 kilometer means this is exactly at the midpoint of the transmission line. That's why the reactive power here will be 0.
Ma'am, if
If
the reactive power at 200 kilometer, 300 kilometer means, then what is the expression of reactive power, ma'am?
so they at 200 kilometer, 300 kilometer, it will not be 0. But only at the midpoint it is 0. If you see the lecture of week 3, you will see that. Just a minute, I written it here. I don't know whether I have written it. Yeah. See, this is the expression of qx. Okay, at any random point, and x is
Ma'am,
a
but I'm
point.
not getting the exact answer when I solving this equation, ma'am.
You will get the exact answer. So what you do is here, what will be x, you tell at midpoint what is
X
x.
midpoint, definitely it will be 400, ma'am.
It will be
If I
400, but
change, if
if
I
you
change the value of x, ma'am, not 400, if I keep 200 or 300, then I am not getting the reactive power correctly, ma'am.
no, you should get the correct. See, first of all, if the total line length is L, and if you put x equal to L by 2, then you will get qx equal to 0 definitely. Okay.
Yes,
If you
ma'am.
just put x equal to L by 2, you will definitely get x, it will be 0. But remember one thing, that this x, the expression that is derived here, this x distance is from sending end, okay? But there may be a question where they, just to trick you guys, they will say that the point is from, suppose 200 kilometer from the receiving end, right? Suppose they say, then what you will have to do is you will have to subtract this value from the line length, and that will be your x. Your x will not be 200. In that case, your x will be 600. Do you get it?
Yes,
So
ma'am.
this x distance is from sending end, not the receiving end. They may say in the question that the point from 200 kilometer from receiving end, you find out the reactive power. Then you can't directly just take x equal to 200. You will have to subtract from 800, because in that case, if this is 200 kilometer from the sending end, then this is 600 kilometer from the 600 kilometer from the sending end, if it is 200 kilometer from the receiving end, right? So this type of tricks they can give in the questions, just to, and this will be just for silly mistake you may do, but otherwise you should get the exact answer if you put the value of x here.
Ma'am, if reactive power is given in terms of percentage, means then how we need to do, ma'am? In
uh,
assignment questions, they ask, ma'am.
yeah, so percentage, that is also, uh, see, if in that is basically per unit, you will have to multiply it by 100. Okay. In some questions, if they give that you take the base power as surge impedance loading, then you can, what you can do is, whatever your q divided by sil multiplied by 100, you will have to calculate. Okay. I think that's what they are, because usually they take SIL as the base power. So that this will be your percentage power. And per unit will be simply Q by SIL. That will be your per unit. Okay.
Okay.
Okay. So if you in your assignment, if you have any particular question that you didn't understand, you can tell me.
week 3 assignment, fourth question, ma'am.
Okay, I don't have the access to the questions of this year. Okay, so can you just mail me the question, or you can write in the chat section. I will discuss in the next class. Okay.
You keep your mail ID, ma'am. I will mail the question.
Yeah. Okay. So yeah, I already gave, I think, the mail ID, but anyway, I will again
Your
give.
chat box is not available, ma'am.
Oh, acha, acha. Okay, okay. Okay, my mail ID is this. I will just write here. This is my Gmail ID. Okay. You can mail me here regarding your doubts. Okay. Yeah. Okay. Okay. So thank you for joining. Uh,
Thank you for your patience, ma'am, for explaining each and every point. When I ask you, never hesitate, and again you try to help me, ma'am. Thank you, ma'am.
yeah, yeah, that's what I am here to do. That is my work here, to make you understand. Okay. Okay, thank you. We shall meet in the next week. Okay. Bye.
Okay, ma'am.
Thank you.
Bye.
Yeah, bye.